In this sequence, we will find our first mutable data structures, which are the arrays. We have met the array data structure back in the course in week 2, sequence 3. That's a very interesting data structure. It has a fixed size, it allows us a direct access to the elements in constant time, and indeed it is particularly well adapted to be used with loop constructs, like the one we have just seen. Let's refresh our memory with a simple exercise. Let's write some code that uses an array to find all the integers which are cubes and also squares. So let's compute these cube numbers which are also squares. First of all, we define a function cubes of n that creates an array initialized with the cubes of each of the indices. Okay. And then we define our own petty function to compute the square root of an integer, and a function to check whether an integer is actually a square. Once we have all this, then computing all the cubes, which are also squares, up to n is not very difficult. It's this function we have here. So you see, basically, we create the cubes of the first n integers, then we iterate over them with the for loops we have learned to use, and if we find one element there, which is actually the cube of the index, which is also a square, we print it, and that's it. Okay, so we can test it on 100, and so you see these are all the cube numbers which are also squares of integer up to 100. Now the good news for some of us is that Okamen's arrays are really real arrays. Not only they can be used, like in the previous example, but they can also be modified in place. We do this using a special operator which is called the update operator, this backward arrow here. And yes, after performing an update, the old value is really lost, as you can see in the following example. Okay, so let's define again an array, 5 elements like this one. Of course, we can access the elements of an array, but now we have discovered we have this new update operator, this reverse error, and we can use this update operator to say that we want to modify the content of the first cell of the array, and we change its content by putting 100 inside it. Okay, as you can see here, the result of the operation is of the unit type, but there has been something done as a side effect. And indeed, if you look again at the content of the first cell of the array, now it is 100 and no longer 0 as before. And actually, if you look at the array altogether, you see it has been modified. Now it is the same array as before, and we didn't create a copy of the array by making up a change in some place. It's the same array that has been modified in place. Well, once we discover that we can update the content of an array as much as we want, and then it can become easy to write operations in the traditional imperative style we are used to in other languages. Like, for example, we can decide to take an array and try to rotate its contents on the left. This is the function rotate we are defining here. You see, it takes an array A here, then it computes the length of the array by calling the array length function. Then it saves the value which is the leftmost, the one in position 0, because it will be overwritten. Then with the for loop that we have learned to use, we shift all the values to the left in one position, and then we restore in the last position the value of the first cell. Okay. So this is something we can pass to the compiler that is very happy. We have defined a new function called rotate that takes an array which is a polymorphic array, no matter what are the elements, and returns a unit type because, of course, there is no actual result there. The only thing we have done, we have modified in place the content of the array, which was passed as an argument. Let's try it out. That's a handy way using array.init to create an array with all the elements from 0 to 10 to 9. You see, now we can decide to rotate this array once. And once we have done the rotation, of course, you see everything has been shifted to the left one pace. We can rotate it again and keeps shifting. You can play the game as much as you want. Well, that was a very simple example of how you can use arrays in OCaml exactly the same way you do it in other programming languages. So a few words on this update operator. It is used for in-place modification in general, so when you see an expression E1, then the update operator, then E2, the expression E1 is expected to denote a mutable value and is evaluated. Well, the type checker actually ensures that E1 is a mutable value, and this mutable value is modified in place, and the new value is the result evaluation of E2. The type of the overall operation is just unit. To sum up, we have seen that the array data type we have used a lot up to now is actually mutable, and the update operator is used to modify in place the cells of the arrays.